Welcome to lecture 4. In lecture 2 we have studied how the soils are formed and what kind of types of soils that exist in our country and of course all over the world. And in lecture 3 we have studied how the soil can be characterized in terms of its three-phase components. We have said that soil has solid, liquid and gaseous phase. Basically solid is mineral grains, liquid is water and gaseous phase is air. Based on that we have defined terms like porosity, void ratio, degree of saturation. These are what we call as volumetric ratios or proportions. Similar to that we have one which is called the water content, and then we looked at the unit weights, the total unit weight, which is what the natural state is. If I dry the soil, if I look at only the weight of soil, it is dry unit weight. Then if it is submerged inside water, we have both saturated unit weight and the buoyant unit weight. We also have interrelationships between all these parameters, which I would like you to work out based on the worked out examples in the books, and lot of practice is needed for you to master the subject. Today in lecture 4, I would like to concentrate on the state of the soil and description of the components. So first we said you have mineral grain. They constitute the solid part of the soil. Now what are they? Basically, if you can look at it, most soils, some particles are visible to the naked eye, but some are so small, some particles are so small, you need a microscope, very small. So you need a microscope, maybe if they are very small, you need even electron microscope. I can say, for example, this is something you can see very easily. Then if I reduce it, it's much smaller, then becomes very small indeed. So what we would like to describe would be the size and the shape of the particles, or shall we say grains. So here, if they are large enough, we have two approaches. We have what is called as the sieve analysis, and the second one is called the hydrometer analysis. If the particles are large, you probably would have seen on the roadside people separating the workers in a construction site. You can separate out large gravel, sand and fines when they are making cement, concrete, etc. Even at home you would see probably your mother, sister, any of them, they do sieving to separate out fine and coarse fractions of, for example, rice, wheat, rice powder, wheat powder, etc. A sieve is nothing but a mesh with a container. As you can see, depending on the number of wires that are put in each direction, the size of the opening is fixed. I can keep 10 wires in a sieve or each direction, or I can put 20, I can put 50, etc. We call them as sieve sizes, and I can have starting from the largest we normally use in geotechnical engineering is 4.75 millimeters, would be the width here I am talking of. That is the largest opening to as small as 0.75 millimeters. This is called the sieve number 4, and this is called sieve number 200. You cannot make it any finer than the sieve number 200 because the particles will start sticking to the wires and they will not fall. So what we do normally is we have the stack of sieves. This of course is a pan. Nothing will go through, but these are all sieves. So I put all the soil here. These are different sizes. Let us say sieve number 4, 10, maybe 50, 100, 200. Then if I put different sieves and start shaking, whatever particle which is greater than 4.75 millimeters will not fall through the first sieve. Then the next size is retained here, third size, fourth size, fifth size, etc. So let us say I have M1, M2, M3 and Mn. What I am trying to say is I can find out, I put say 100 grams of soil, find out what is the weight of soil retained on sieve number 1, which is sieve number 4, the topmost sieve. M2 is the amount of soil retained on sieve number 10. M3 is amount of soil retained on 70 size or 60 size, 100, 200, etc. So what is the total amount of soil that has been used here? M1 plus M2 plus M3, M4, like that. I can go up to Mn. Let us say this could be 8 grams, this could be 14, this could be 6, 11, 18, etc. So that will give me the total weight of the soil that has been put in, and that is retained by different sizes. Is it clear? What we are saying is we'll take a certain amount of known amount of soil. Doesn't have to be 100 grams or 200 grams. It could be approximately about 100 to 150. We put it here. I take the initial weight, but because of the dust, the final weight may be slightly different from the initial one. I put that in the top sieve. Then I shake the whole assembly and then find out how much weight of the soil is retained on each sieve. I take the soil retained on the sieve, put it in a pan, take it to the balance and measure it. Then I'll find M1, let's say 6 grams is retained on the topmost sieve, which is a 4.75 millimeter size, maybe 11 grams, 18 grams, 16, etc. Then we try to calculate what is called as percentage retained. So can I say sieve number and percentage retained on each sieve? How do I get it? If I want to say for the first sieve, percentage retained on number 4 is equal to the total weight of the soil minus M1 will give me divided by M as a percentage. Let us say you have put in 100 grams and 5 grams has gone in. So you have 95%, 95 divided by 100. So this will be, let's say this is 100 minus 6 by 100. So this is 94%. Can I say that 95% of the soil passes through the particular size? So that is percentage, I'm sorry, I should say percentage finer. So I can say 94% passes through that. That means 6% is retained and 94% passes. Similarly, if I want for the second one, I can do, this will be, let us say we said this is 6 grams, this is equal to 11. So then it becomes, in the second one, percentage retained is 6 plus 11 grams, or percentage passing through is equal to 100 minus 6 minus 11 by 100. That is 83%. So corresponding to this size of, let us say, maybe 1 millimeter, the soil is 80%, 83% is finer. So like this, we can get the distribution of the different particle sizes. Please remember, the grains may not necessarily be equidimensional, but usually sands and gravel, these are called coarse grain soils. They are relatively equidimensional. By that I mean, if I look at a block like this, I have one dimension here, the second dimension is the thickness, third dimension is the height. They may not be exactly same, but they are of the same order. This could be 1 millimeter, thickness could be 0.8, the height could be maybe 1.5 millimeters. Something like equidimensional, that's what I mean. Again, another example would be one dimension here, second dimension here, third dimension. Don't look at it, the actual size could be much smaller. This is the characteristic of coarse grained material. So what it means is, suppose I have a slightly longish particle. If the two horizontal directions are the same, the particle can go through. So what it will tell you in terms of sizes is, what is the size through which a grain can fall through, and that will give me how much is passing through the size. So I can have a table now. Shall I say percentage finer? I can have sieve number 4, 10, 20, 50, 100, 200. Everything passes through, so it may be something like 95, 87, 65, 42, 31, maybe 18. So you can get different sizes of particle distribution. Each sieve number has a size. This is, as I said, 4.75, and this should be 0.75 millimeters. Please remember, these are very standard numbers. So you can say the largest is 4.75 for sands, and the smallest is 0.75 millimeters. So you can see different sizes here, and you will get the standard size distribution from the textbook or from any Indian standard. What you can then do is plot a graph between the particle size we call it a symbol D, and we use a log scale here, not a linear scale. Let's say I'm using not 1 millimeter, not 1, 0.1, 1, and 10. You may go up to maximum 100, which is for sizes bigger than gravel. You can call cobbles or boulders, etc. Here I'm talking a percentage finer. It goes from 0 to 100. If every particle goes through, this could be 100. Suppose the maximum size of the particle is less than 4.75 millimeters, all the soil will go inside, so percentage finer. Then I can plot all these points. And draw a graph, something like this. This is called particle size distribution curve, or we say grain size. What you can do this from sieve analysis is from 4.75 to 0.075 millimeter range. I can simply put it on a sieve, shake the soil, collect the amount of material retained, and then I can find out how much is passing through. percentage finer or percentage passing through. And plot it against the size. How is the size determined? From the sieve number, you can get the particle size. As I said, you look into a table. We don't need to waste time on listing them here. You can copy it from a book, or when you do the experiment, you can write it in your report. From that, I get a graph of this kind, and I can also identify this I call as D50. What does it mean? At 50% of the soil is finer than this particular size. Or I can say maybe something like this. This is D10. I can get D60, D30. Whatever size I want, I can get. What it means is when I say D10, D50, D30, etc., the particular size determines what is the percentage finer than that fraction or size. So, for example, if D50 is 0.15 millimeters, 50% of the soil is finer than 0.15 millimeters. So, these are some of the parameters you can get from the distribution curve. I'll come to some definitions with respect to them a little later. But my next point would be, what do I do for particles finer than 0.75 millimeters? If the soil is very fine, very small, as I said, you cannot even see with naked eye. We may need a microscope to see. But I cannot count them. How many are there in, say, 50 grams or 100 grams? So we use a very simple principle of hydrometer analysis, and the principle used is Stokes' law. What Stokes, a physicist, studied sometime long time back would be, if I take a jar of water or any liquid, let us say you put in a particle or any material, ball or whatever it is. As you can see, if I put it here, it starts falling into the liquid. The velocity with which it falls, initially the velocity is 0, and if I now plot with respect to time, velocity, it immediately picks up speed, but there is what is called as a terminal velocity. The velocity with which, so what we normally do is, we assume that this time is so small, neglect it. So we assume the particle starts falling with the terminal velocity, because the inaccuracy by neglecting this T0 is not much. What you find very interestingly is that this terminal velocity, if I call it as V, V is a function of the diameter, the density of the fluid, density of the particle and the fluid, and viscosity of the fluid. In fact, if you would like to know the equation which is given by Stokes, I can write it down. V is equal to rho solid minus rho fluid by 18 eta into d square. As you can see here, this is the density of the solid, the particle that you are putting in. In our case, we know that it's equal to G times density of water. This is rho fluid. We are using all the time water, so I can replace this by rho water. Rho solid is G into rho water, and eta is the viscosity of water. So the velocity is proportional to square of the size of the particle, the diameter or whatever it is. The larger the particle, the faster will be the velocity. So can I say, if I now ask you to visualize, instead of one particle, I put in soil of different sizes. And this is a usual jar you find in a laboratory, 1000 cc jar. What we do is we take some 25 or 50 grams of soil, mix it thoroughly, and put the suspension. You can see that initially all the particles are uniformly distributed. After a time of 1 minute, I'll find that all the large particles will settle. After 10 minutes, another set of particles will completely settle. After 100 minutes, some more. The finer the particle, the slower is the velocity from this equation. And finally, we wait up to 24 hours and expect all the particles that are likely to settle will settle. And the smallest fraction, obviously, is somewhere around 0.01 to 0.02 millimeters. Can you say why? Because you know that a colloid is defined as, in physics again, particle with 1 micron or 0.01 millimeter. Any particle of the size of 0.01 millimeter or finer will never settle, and that is why we call it as a colloid. So what you find is somewhere around 0.01 to 0.02, the particles will not settle, they will always remain in suspensions. So what does hydrometer do? It tries to give us the particle sizes from 0.75 to 0.02 millimeters. And how do I find out? I had to, for example, after every time reading, I take a small sample and find the weight of soil. Initially, let us say there are 50 grams in 100 cc or 1000 cc. After 1 minute, I can find out. So I know all the coarse fraction has fallen. After 10 minutes, I get another reading. Instead of taking samples through a pipette and doing it, we have what is called as a hydrometer. I don't know whether you have seen it before in your physics. It's a very simple device which measures the density. So if I have a fluid, here is the suspension. I put in a hydrometer and I take readings. It gives me the density, and density is nothing but a proportion of the soil. So hydrometer, it has the readings, say somewhere here it will be 1, and this should be something like 1.03 or whatever it is. So if the density of the fluid is high, the hydrometer will be floating in it and you get the maximum reading. As the density of the fluid decreases, the hydrometer sinks down and you get a smaller reading. So at different times, t, say I start with t0 in minutes, I get 1 minute, 5 minutes, 10, 30, 60, I go on up to 1 day, which is 1440 minutes. I take the reading of density, which will start with say 1.32 and goes on decreasing to 1.005. You know the density of water is 1, so by the time you get a small value. Using this, again we try to calculate the percentage finer, so that now I can complete the distribution curve, grain size distribution curve. As I mentioned, we are going to plot percentage finer and d particle size, d in millimeters, and you will have, it goes from 0 to 100. This one goes from 0, 0, 1, 0, 1, 0.1, 1, 10, etc. And I can draw a graph like this. And what we find here is from here to here is through hydrometer analysis. I'm sorry, here. And from here to here would be sieve analysis. So you have a complete distribution of particle sizes. Now I can show you clearly. This is D10, D50, D60, and of course somewhere else we use D85, and in some other designs we need D15 too. I can get different sizes corresponding to percentage finer. We define two terms, what is called as uniformity coefficient Cu is equal to D60 by D10. 60% finer, this is 50, this is 60, and this is 10. I can take the size corresponding to 60% finer and size corresponding to D10. I take a ratio. It will tell me. The smaller this ratio, which means D60, suppose this is equal to 1, which means particles are of the same size. If the ratio is larger, then the curve is spread and you have different sizes. Another would be coefficient of curvature. We call it CC is D30 square by D10 into D60. This is another parameter we use to describe the curve. And this is how we talk of the kind of soils that we have in terms of gradation. Now we'll describe how we classify the soil into different components. You might have heard the names called sand, silt, and clay. Gravel, sand, silt, and clay. These are the names you would hear. These two are called the coarse grained, large size, coarse grained soils, and these are called fine grained soils. Here gravel has something like say 300 millimeters to 4.75 millimeters. Sand is 4.75 to 0.75 or 76 millimeters. Silt size is 0.76 to, and anything less than 2 microns is called clay fraction. This clay doesn't settle at all. Silt is finer than this. It can have silica or any kind of grain. Sands and gravels is what you can see. In this again we distinguish as coarse, medium, and fine sands. So depending on the range you have different sizes, and silt we don't talk of any finer classification. This is how you do that. Now the feature here is sands and gravels are very large, so they are easily visible and we can distribute the sizes. Silt I can measure by means of hydrometer. I cannot do anything about the clay. I know it's a very fine particle, so we can't do much in terms of measuring the size. But they have one very interesting characteristic. When you add water, the behavior changes. So for fine grained soils, in order to characterize them, we try to determine what they call as consistency limits. These were identified by an agricultural scientist called Atterberg. The most interesting part of fine-grained soils is effect of water. They can, if you add water, the fine-grained soils behave like a liquid for a large percentage of water. If I start decreasing the amount of water, it behaves like a plastic material. If you have seen a potter, what he does is he keeps on adding water so that the soil is of right consistency so that he can make a pot or a container or whatever you have with the mud. If I even decrease it further, it can become almost like a solid. What is the characteristic of a solid? A solid has a finite volume and finite shape. If I say this is a solid, it has certain volume and shape, you can't change it. Whereas soil is one material whose volume and shape can be changed. So when it finally becomes fairly dry, it behaves like a solid. If you increase the water content, I can then mold it into any shape. That means it behaves like a plastic material. If you add any large amount of water, you can even make into a suspension. But we are not interested in a suspension. What we would like to know is what is the maximum water you can add before the soil loses its shear strength. So we define what you call as limits. Can I say liquid? Then it is semi-solid, or shall I say this is the liquid limit. Then it becomes plastic. So you have plastic limit. And then semi-solid. We have what is called as the shrinkage limit. And finally, solid. What it means is here, you remember we defined yesterday the water content. If the water content increases, a certain limit is reached. Beyond that, if you add more water, the soil behaves like a liquid. If I now reduce it up to a certain limit, we call as plastic limit. I can put liquid limit here. In this range, the soil can be molded like any plastic material. And then if I now reduce the water content, it becomes more like a semi-solid. After the final one, which is shrinkage limit, even if I remove water, the volume will remain exactly the same. So these are the three limits we have to characterize fine-grained soils. Please remember, what are they? Fine-grained soils are silts and clays. So we need to find out what are the limits so that in practice, suppose you determine the water content, you can say it is in between plastic limit and liquid limit, or below plastic limit, above shrinkage limit, etc. So the whole idea is to describe the state of the soil as a civil engineer. It will fall in one of these. If it is higher than this, we are not interested, because the soil becomes a fluid, and then it becomes a sediment and may start flowing, etc. To do that, finish? Time is over? Oh, that's okay. I can still. We determine liquid limit by what is called as a Casagrande method. He has taken a cup, steel cup, filled it with soil, makes a groove, and then this cup is lifted and dropped by a distance of 1 centimeter. Then you find that because the soil is so soft, it tries to close. And we count the number of blows to close the gap. And that we plot here. I can determine what is the water content. I mix soil with different percentages of soil, put it in the cup, make a groove, drop it number of times, count the number of blows. Suppose the water content is 35. Number of blows may be something like, say, 11. Then this is 27%. This becomes 18. Then this could be 19, the number of blows may be 27, and this is about 12, and this becomes 37. As you can see, as we reduce the amount of water content, the soil is becoming stronger and I need larger number of blows. I plot here the number of blows against water content. So I'll have points, I draw that, and the definition is 25 number of blows. And this will give me the liquid limit. If the groove closes when the number of blows is 25, that corresponds to the smallest measurable shear strength beyond which it behaves like a liquid. So that is called the liquid limit. Another technique developed was cone penetration. Wherein we put in a cone on a small cup and we look at how much water content you have 20 millimeter penetration. Okay. So these are the two methods whereby you can determine the liquid limit. You will probably carry out the test in the laboratory and you will get a better feel for it once you do the test. The plastic limit is a little different in trying to determine. I take a pat of soil, a small piece of soil, and then I try to roll it something like this, so that I get a thread, and when the thread breaks, say this is the thread, you can make it finer, but once you reach something like 3 millimeters, if it starts breaking, that means it's becoming brittle. That is the plastic limit. So what I'm saying is, you add water, different percentages. When you have high water content, you can make into as small a thread as possible. If you have too small, you cannot make into a finer one. So I keep trying to adjust the water content such that the thread at 3 millimeter size will start breaking into smaller pieces. So that means it's becoming brittle that means it's not plastic. So this is a kind of empirical way. You have to keep trying it till you get a correct size, and that will give me the plastic limit. So we have shrinkage, liquid limit by Casagrande method, and plastic limit by rolling a thread into a small, we call this as. Now to determine shrinkage limit or to define it, suppose I have water content versus volume. You find that as you decrease the water content, the volume continuously decreases and becomes constant after a certain water content. That is called the shrinkage limit. We add water to the soil sample. As I keep removing, let's say I'm putting it in an oven and heating it, as the water evaporates, I also find that it keeps shrinking. You can make a ball and leave it in the sun, and you will see that the size of the ball or the pad decreases, but after a certain stage, the volume more or less remains constant. So what we do is we take a cup, fill it with moist soil. I know the initial weight. I can take the weight of the soil in the cup. I also know the size of the cup, so I know the volume. After keeping it in the dry thing for about an hour or two, in the evening we put the same cup in an oven and heat it to 105 degrees centigrade for 24 hours, and then you will suddenly see that the soil shrinks and becomes a small pad. So this is the driest volume. It cannot shrink any further. I can find out the weight here. I need to find out the volume of this, which is a little tricky because it's not a regular shape. It's not a cylinder, it's not a cube, it's very uneven shape or irregular shape. So what we then do is we immerse in mercury and find out. I put the whole thing in a mercury container, and then I can find out how much mercury surrounds the particle. I know the volume of the cup. I remove the volume of mercury, then I get the volume of the pad. From there we calculate the shrinkage limit. So we can find out all three. This is by using what you call as mercury immersion method. So we can now determine the shrinkage limit, which is, we have another very important parameter called plasticity index, which is, we write it as PI, or some people write as IP, which is nothing but liquid limit minus plastic limit. What does it tell me? It is the range of water contents over which the soil behaves in a plastic state. That is very important in terms of characterizing fine-grained soil.